Good morning, Panthers. It is Dr. Augustine. I hope you all are doing well. I am going to be covering the middle sections of Chapter 9. We're going to cover about covalent bonding, the Lewis diagram model, talk about the bonding continuum ranging from ionic bonding to covalent bonding, and then also a little bit about electronegativities, bond polarities, and polar versus nonpolar covalent bonds. So chapter 9, this is a really key chapter. If you're planning on going on to organic chemistry, this is actually arguably one of the more important chapters in all of Gen Chem 1. So let's get started. First of all, chemical bonds are complicated, but we'd like to come up with models to help explain what different types of chemical bonds there are. So we talked earlier in the semester about 3 different types of bonding. And they involve what actually is bonded together. So the first type is called metallic bonding, and that consists of metals bonded to other metals. We actually don't spend very much time on metallic bonding in general chemistry. You can wait for an inorganic chemistry class if you're really interested in learning more about that, or maybe perhaps a material science class. The second type of bonding is called ionic bonding, and this is between cations and anions. And if you remember from earlier in the semester, we said that things on this side of the periodic table, on the left side of the periodic table, reacting with things on the right side of the periodic table, those form ionic bonds, cations and anions bonding together. And the third type is called covalent bonding. All right, co means together, valent having to do with the valence electrons. So sharing the valence electrons with one another forms covalent bonds. So in the early 1900s, as our understanding of chemical compounds was improving, a chemist named Gilbert Lewis discovered or proposed that a way to explain how atoms would come together and form chemical bonds would be with a very simple model that involving these dot structures. So these are shown over here in this figure. And the idea behind these is each element has its own Lewis dot diagram corresponding to how many valence electrons it has. So for instance, sodium has 1 dot, and carbon has 4 dots corresponding to 4 valence electrons. Now this is not taking into account how they're arranged in the s orbitals or the p orbitals or anything like that. It's just counting how many dots each element has. Fluorine, you notice, has 7 dots. And then the guys on the end, the noble gases, you notice they all have 8 dots around them, or 8 electrons around them in their valence shell, except for helium, which has 2. So this is an important idea then. These noble gases have what Lewis called an octet, or a complete 8 electrons around the outer shell. And then his simple model was to say that elements want to form these complete octets. And once they form these complete octets, then they're happy. So for instance, if we have sodium with 1 dot and fluorine, and I'm going to use a different color dot for the showing it's from fluorine, then both of them are going to end up being happy. Fluorine's going to have 8 electrons around it. Sodium is going to share its electron, and where it shares those electrons is going to be a chemical bond. This, of course, we know as an ionic bond. Now you might be saying, well, wait a minute, sodium doesn't have 8 electrons because it only has 2 electrons around it, but remember, this is actually a sodium ion, right? So it's actually Na+, which means that electron is being given up to the fluorine. So the fluorine has a complete set of 8 electrons around it. It's actually F-, and this is actually Na+, which means the Na now has the electron configuration of neon, which is also a complete octet. So for an ionic compound, when you give up those electrons, you end up with the octet around each atom again. All right, so it's a simple way of using this octet idea as being a particularly stable thing that nature likes to form. All right, so where Lewis's idea got really interesting is it became a very powerful way of explaining how covalent bonds could form. Ionic bonds kind of make sense. I mean, one gives up its electron to be a plus, makes the other one a negative, and everyone's happy because they have a noble gas configuration. But Lewis's idea gets really interesting with compounds that are covalent compounds. So for instance, something like CH4. All right, and if we take carbon, give it 4 valence electrons, and we have hydrogen with 1 valence electron, then if we count up how many electrons we have at the end of the day, we have 2, 4, 6, 8 electrons around the carbon. It forms this nice octet, and then hydrogen actually gets 2 electrons around it. Remember, hydrogen only has a 1s orbital to fill, right? 1s, and it only needs 2 electrons. So now suddenly everyone's happy because it is fulfilling the octets around the carbon and around the hydrogen. Very simple way of explaining what the configuration of a CH4 might look like. And in fact, we can replace these dots with lines once we have them written. So carbon, every one of those 2 electrons we can write with a single line. So that notation, those 2 electrons becomes that single line. We call this a single covalent bond. All right, so my Lewis structure then for CH4, which is methane, is something like this. And the powerful idea that Lewis has proposed is we can use this very simple model to help us explain how things will arrange themselves in terms of chemical bonding. And it turns out the CH4, the methane molecule, actually is a carbon attached to 4 hydrogens and with 4 single bonds. So Lewis's very simple structure, or very simple idea, has given us the correct structure of a methane molecule. Now, this is probably a high school level example and probably one you've had before. I'll give you another high school level example. How about something like H2O? So we've got an oxygen, it's got 6 electrons and a hydrogen. Each of the hydrogens has 1 electron, and then we end up with something like this. And remember, every one of those pairs of electrons we're going to replace with a line. So we're going to end up with something, whoops. That looks like this for our Lewis structure. Now we've got something that's a little bit different. Now we have these extra electrons. We call these lone pair electrons. So H2O has 2 sets of lone pairs. And again, you notice if we count these, we have 2, 4, 6, 8 electrons around the oxygen and 2 around the hydrogens. All right, so this is a couple of principles I want to highlight then. We have this idea that we call the octet rule. And this is that atoms want to get 8 electrons around them, unless they're hydrogen, which they're going to have a duet. They're going to have 2 hydrogens around it. So hydrogens are going to have 2 electrons, and the central atoms are going to have 8 electrons. That's the way they're going to tend to bond. And we have bonding electrons, like in this case, these covalent bonds. We also have lone pair electrons. Okay, so we've taken a look at 2 different molecules, CH4 and H2O. We figured out how to write the Lewis structures of these. We've seen single bonds. We've also seen lone pair electrons. Let's go to a slightly more complicated example, something like carbon dioxide. And this is one that would not work quite as well with your high school idea of just simply taking this Lewis dot diagram and immediately turning it into a Lewis structure. That works for a couple of different things, but it actually is not a generally good way to write Lewis structures. So for carbon dioxide, we can create an octet by creating a double bonded pair of atoms to the carbon. And if you count them, we have 2, 4, 6, 8 around one of the oxygens, 2, 4, 6, 8 around the other oxygen. All right, so 8 electrons around this oxygen, 8 electrons around this oxygen, and then 2, 4, 6, 8 around the carbon. And the octet rule is satisfied for the carbon. So what do we call these? Let's erase all these markings I've just made. Oops. We call these double covalent bonds. And we can also have a triple covalent bond, something like C2H2. That's what the Lewis structure looks like for C2H2, and this is a triple covalent bond. All right, remember, each line represents 2 electrons. So if we're counting electrons, we go 2, 2, 4, 6, 8 around that carbon, 2, 4, 6, 8 around that carbon, and then we have 2 around each of the hydrogens. The duet is satisfied for each of the hydrogens. So the octet rule, again, is satisfied. So we use this idea of the octet rule and the number of valence electrons to help us figure out how we can write an appropriate Lewis structure. And what this is telling us, the important piece that this is telling us is we have one carbon attached to another carbon, which is attached to a hydrogen, and they all form the molecule in this way. There's no other way to arrange this molecule where the octet rule is satisfied for everything. All right, so before we do give you a systematic model or a generic model for writing Lewis structures, I want to talk a little bit about polarity and electronegativities in a bond. And then then we'll have the tools to write Lewis structures and understand a little bit more about them. So if we have a molecule like HF, and we use our dot structure to write this. So fluorine has 7 electrons around it, and the hydrogen has 1 electron around it. If we look at the valence, or we count the octets, we have 2, 4, 6, 8 around the fluorine, and we've got 2 around hydrogen. So that looks good, right? We've satisfied the octet for all these. And remember, we can replace these 2 dots with a line. So we'll get something that looks like this. This would be the Lewis structure for the HF molecule. Okay, nice simple one. That's probably a high school level problem. So you notice that we have a hydrogen attached to a fluorine. And we also know that fluorine likes to have a negative charge. We know that hydrogen doesn't mind having a positive charge. So it turns out that in nature, that we have this property called the electronegativity. And here's the definition of electronegativity. Electronegativity is the desire for an atom to have extra electrons in a chemical bond. Let me say that again. Desire for an atom to have more electron density in a chemical bond. It's similar to electron affinity in chapter 8, only that's just the atom itself. This is the atom in a chemical bond. So here's a good example. We have a chemical bond. We have an HF molecule, and we have hydrogen and fluorine. And if we look on this table, this is a trends in electronegativity. We look on this mapping of electronegativities versus element. We notice that fluorine has this number 4.0, which is a very highly electronegative element. In fact, if you look at these 6 elements, have the highest electronegativities: nitrogen, oxygen, fluorine, chlorine, and bromine. Those have very high electronegativities. Hydrogen has electronegativity of 2.1. And you notice these guys down here, francium, cesium, rubidium, they have very low electronegativities, potassium, nitrogen, or excuse me, sodium. They don't want extra electron density, and the guys on the right side of the periodic table do want extra electron density. So you can clearly see that the trend goes something like this: increasing electronegativity as we go this way, and increasing electronegativity as we go left to right across the periodic table. So as we go up the periodic table, the electronegativity increases, and as we go left to right, the electronegativity increases. All right, what does that mean for a molecule like HF? What that means is that the fluorine wants the extra electron density from hydrogen because the electronegativity is so much higher in fluorine than it is in hydrogen. And the net effect is that the electron cloud ends up looking something like this. In fact, here's a better picture of this for something like HF. So this would be the hydrogen end of it, that would be the fluorine end of it. All right, and remember how we draw these circles. That means that 90% of the electrons are contained within that drawing. So we notice we have extra electron density on the fluorine side of the molecule. We have some notation that we use for this. We can put a little minus sign, delta minus sign, on the negative side of the molecule and a little delta positive sign on the positive side of the molecule. And what that means is there's a partial charge. It's partially positively charged on the hydrogen side, partially negatively charged on the fluorine side. Another notation we can use is we can use an arrow with the arrow pointing towards the negative side, and we put a little plus sign on the positive side of the arrow. And that arrow points towards the direction where we have the positive side. We call this a polar molecule. And we call the bond a polar covalent bond. All right, so that chemical bond right there, that covalent bond is called a polar covalent bond, and the entire molecule is called a polar molecule because there is permanently built into the molecule a partial positive and a partial negative side to the molecule. We also call this a dipole, where we have this scenario where we have a positive and negative charge. All right, so how do we determine whether something's polar covalent or not? It's quite simple. What we use is we use the difference in electronegativities between atom 1 minus atom 2. All right, in this case, it would be 4.0, that would be the fluorine, minus 2.1, that would be the hydrogen. So that's going to equal to 1.9 is going to be the change delta electronegativity. And then we can use this figure right here to help us figure out whether this thing is a polar covalent bond or not. So if we have between 0.4 and 2.0, we call that a polar covalent bond. If it's from 0.0 to 0.4, we call that a non-polar or purely covalent bond. And 0.4 happens to be the difference between hydrogen and carbon. So if it's from 0 to 0.4, we call it a purely covalent. 0.4 to 2, we call it a polar covalent. And if it's more than 2, up to 3.3, we call it ionic. And we say that it's actually given its electrons up. You notice it's actually a continuum. There isn't a sharp cutoff, but arbitrarily we say that 2.0 and above, we call that an ionic bond. So we can use these differences in electronegativities to tell us whether it is ionic, polar covalent, or purely covalent. So let's just take a look at the molecules that we had up above. This carbon-hydrogen bond would be purely covalent, and in fact, every one of those we would call it purely covalent. The oxygen-hydrogen bond, so oxygen has an electronegativity of 3.5, hydrogen's 2.1, that one's going to be a polar covalent. Oxygen-carbon, 2.5 to 3.5, that's 1. That's also a polar covalent bond. Hydrogen-carbon right over here, this is purely covalent. And anytime you have an atom attached to the same atom, carbon-carbon, it is by definition going to be purely covalent. So purely covalent, this entire molecule, purely covalent. This one is polar covalent, and these two bonds are polar covalent. And what we're looking at here is the actual bonds. We call them polar or purely covalent. All right, next video is going to give us a systematic way of writing out Lewis structures, which is hopefully more robust than the way you learned in high school.